Hello. In this video, we're going to be counting up a number of possible outcomes given a certain situation. Now, this first example, a permutation, is used when order does matter in which things are selected. And I gave an example here. If we elect 5 people to be on the student council out of 12 applicants, and the reason that the order matters is because they can hold different positions. So when we have 12 applicants, there are, let's say the first position we elect is president. Now, there are 12 different people to choose from to be president, then 11 people to be vice president, then 10 to be, let's say, secretary, treasurer, and historian for the last elected position here. Now, the way we can count up how many different outcomes there are here is by simply multiplying these numbers together. And this totals out to 95,040 outcomes. There are 95,000 different ways that we can select people out of 12 applicants to be on the student council and what positions to hold. Now you can see we have a formula to represent this. It's n permute r, where you're taking n elements and choosing r of them. And we have these exclamation points here, and I'll remind you that the exclamation point means, or is read as, factorial. And when we talk about a factorial, it means all the numbers lower than that number up until 1 that are multiplied together. So for instance, 4 factorial is the same as 4 times 3 times 2 times 1. So to apply this to my example from above, well, we have 12 elements, and because order matters, we use the permutation, and we're choosing or selecting 5 of those people. So we have 12 factorial over 12 minus 5 factorial. So these are all the numbers between 1 and 12 multiplied together, and the bottom is all the numbers between 1 and 7 multiplied together. So I could do 12, 11, 10, 9. I'm going to keep going here. These are all multiplication. That's the top, 12 through 1. And then the bottom, 7, 6, 5, and so on. And the neat thing here is that if you notice, 1 divided by 1 cancels, 2 divided by 2, 3, 3, 4, 4, and so on, all the way up until 7 cancels. And we're left with 12, 11, 10, 9, and 8 all multiplied together, just like we had up here. And so that still works out to be the 95,040 different outcomes there. Okay, so that's an example of permutations. Let's talk about combinations. Combinations are used when order doesn't matter of selection. Okay, so order does not matter. And so if I randomly draw out of 12 entries 5 people to be in a contest, let's say to win a new car, out of those 12 entries, 5 people were selected, and it doesn't matter the order in which they're selected, they just now get to compete. Okay, so it doesn't work quite the same as permutations because the order doesn't matter, because it doesn't matter if you were selected first or if you were selected 5th. So we use this formula down here, n choose r. N is the number of elements taken r at a time. So when we do this with our example here, we have 12 choose 5. And so we'll do 12 factorial over 12 minus 5 factorial times 5 factorial. So we end up, and we already did this piece, the 12 factorial over 12 minus 5 factorial. So we should end up with 12, 11, 10, 9, and 8 all multiplied together when we cancel out the 7 through the 1, or excuse me, the 6 through, the 7 through the 1 on those. And then the bottom becomes 5, 4, 3, 2, and 1. And so let's work on crossing things off again before we actually do any multiplication here. 5 and the 10 cancels, we get a 2. I can do the same thing with 4 and an 8. Can do something similar with the 9 and the 3. And then this 2 and let's say that 2 go away. So I'm looking at 12 times 11 times 2 times 3, which results in 792 different outcomes. So notice that there's significantly fewer different outcomes, even though the numbers 12 and 5 stayed the same, only because the order didn't matter this time. So we could have in the previous example the same combination of 5 in a different order, so like the same 5 people, but in the different order of president, vice president, and so on, where here it didn't matter if we have the same 5 people, whether person A was chosen first, fourth, third, fifth, whatever, it doesn't matter as long as that person's in. Okay, so that is counting outcomes depending on whether order does or does not matter with permutations and combinations. For now, we are done.